Up to now, we've been doing congruence informally. So what we've been doing is we've just been noting congruent angles and sides and concluding that triangles are congruent. But there's also a more formal way to do this using two-column proofs. So we're going to go through a couple of examples of congruent triangles, of proving triangles to be congruent using a more formal two-column proof method. So in this first example, we're given that side AB is equal in length to side BC, and that D is the midpoint of AC. And from that, we are going to prove that triangle ABD, the triangle on the left, is congruent to triangle CBD, the triangle on the right. So let's see how we do this. We write down our givens first. The measure of AB equals the measure of BC, and also the other given is that D is the midpoint of AC. And these are not particularly difficult proofs, so I think in your own mind you should have a fairly good idea of where we're going to be going with these. Certainly one of the first things we're going to do is to use the definition of midpoint to prove that the measure of AD equals the measure of DC. Okay, so we know that AD equals DC because of the definition of midpoint. Okay, so to make it a little easier for us, we could make some notches, 2 notches on each of those sides to remind us of which are the congruent sides. And so far we've got side, side, and side, side. We do not have any angles. You notice that the next step is blank. We don't have either the statement or the reason, but the statement after that is going to be that ABD is congruent to CBD. So the missing statement in some way has got to complete one of the criteria for congruence. So we're either going to find, since we have 2 sides, and either we're going to somehow prove this is a right angle. Okay, that's one possibility, because then we would have hypotenuse side. Or we're going to get a third side congruent, which would give us side, side, side. Or we're going to get angles A and C congruent, because that would give us side, angle, side. So I'm thinking ahead to what are the possible ways that we could end up proving these triangles congruent. And thinking about those 3 possible ways, is there any idea that you have as to what we could do to prove these 2 triangles congruent? So I hope that maybe what you thought about was that BD is a shared side. So BD is both in the first triangle and in the second triangle, and so that means that we've got a third congruent side because BD is congruent to itself. Or we could say the measure of BD equals the measure of BD, and that's because of reflexivity. Okay, or the reflexive property of equality, you could call it either one. We could denote that by an X mark. So the side is congruent to itself. Now we have side, 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 side. We have 3 sides, 3 corresponding sides, congruent to 3 other corresponding sides between 2 triangles, and we can conclude that triangle ABD is congruent to CBD. And you'll notice that A corresponds to C. That's why A and C are both first in here, and the congruent statement, because A is adjacent to both the 1 and the 2 marked sides, and C is also part of the 1 and the 2 marked sides. It's between them. So basically we've got side, 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 and we've got our proof complete. Now you might get this as a problem without being a 2-column proof, in which case you just note to yourself that, well, a midpoint means these 2 sides are congruent, and this side is congruent to itself, so we've got side, side, side. So this is sort of a more drawn-out way, but it offers a more formal approach to proving triangles are congruent.